Let's start. Good afternoon, all. Today we have the 10th lecture in the series of statistics in research methodology. Let us quickly summarize whatever topics we discussed till date. Initially, we started getting familiarized with the subject of statistics, its utilities in daily life as well as research, measurement of physical quantities and the parameters affecting the measurement, and the way to represent the results of measurement appropriate way, along with the accuracy and precision of these measurements, to ways to improve them by understanding the importance of significant figures, place value of digits, rounding of rules, error propagation, and the different types of measurement errors, namely gross, systematic, and random errors. And we concluded that since random errors are inevitably associated with any measurement, how to address them so that we can minimize their effect in the final data of measurements. For that, we have understood the properties of Gaussian distribution in detail and applied it to understand the characteristics of repeated measurements. Further, we went ahead to understand confidence level, confidence interval, and confidence limits of the mean value, which is the measured value, so that we can encompass the true value within the specified limits. Later on, we discussed the discrete and continuous probability distribution functions and their properties applicable for the utility in terms of statistics. Further, hypothesis testing. Initially, we started with uncertainty statistics. We understood the different types of errors, type 1 and type 2, affecting the hypothesis testing, the flow diagram to carry out the hypothesis testing, and the various intricate steps involved in each to carry out that measurement as well as the hypothesis testing, how to infer the data from this hypothesis testing, how to channelize the measurement so that we can improve the quality of the data. Further, we understood the minimum number of replicate measurements in order to get quality analytical data, the reliability interval, the distribution functions like chi-square, and the test to conduct whether the observed variance is due to the statistical fluctuations or there is any significant difference, whether there is a systematic deviation from the expected or predicted variation. Then we had went ahead with the variance ratio, that is F-test, and in the last class we discussed further utility extension of the F-test in terms of analysis of variance, ANOVA, then the product moment correlation coefficient, and the regression, the basic least square fitting was the last topic we discussed in the previous lecture. We start from the point where we stopped in the previous lecture, basic least square fitting and utility in understanding the this calibration function. Normally, instrumental calibration is carried out via the least square fitting, and especially we apply the linear least square fitting method to conduct the experiment. This was the numerical we left in the last class. In the end, you all might have given a try to do this problem. It is very simple. The data, input data says that a few set of measurements on the absorbance of a particular series of silver standard solutions were made by around 7 people by a particular technique, namely flame atomic absorption spectrometry. The absorbance values and the corresponding concentrations are tabulated. From this, we can construct the calibration curve and derive what will be the confidence limits for the calibration functions, namely the intercept and slope. Nowadays, people use more or less frequently the computer softwares like Excel or Origin to get the calibration function. You also can do the same way. Input the concentration values, that is an independent variable, then the output that is absorbance values, then plot them and derive the functional relationship. Essentially, when we do it apply for measurements, we go for linear least square fitting. That is the ordinary, other names are ordinary least square fitting or basic linear fitting, basic least square fitting. As there are 7 input data points, the degrees of freedom comes out to be 7 minus 2, that is 5. 7 number of measurements are there. We have discussed in detail in the last class that degrees of freedom will be total number of data points minus 2, as it is a linear function involving two coefficients. The coefficient of the power independent variable to the power 0 and independent variable to the power 1. These two coefficients. And the Pearson's R, that is correlation coefficient, R square value, and the adjusted R square we will discuss in the coming slides. From that, we have to take help of the T table, wherein you have to go check it with the T tables are already discussed well in advance in 4th or 5th lectures. You can read the T table like at 95% confidence level corresponding to 5% significance. That is nothing but 0.05 value of alpha. Since degrees of freedom is 5, T value, critical T value will be T5 0.05. From the tabulated values of T, you will see that it comes out to be 2.571. Utilize it, and the confidence limits are defined as that value plus or minus T times S. Okay, so T times S are calculated, and thus you can come out with the confidence limits of the interval as well, intercept as well as slope of the calibration function. The narrower the confidence interval, the better is the precision or the quality of the measurements. So just by seeing the relative confidence interval with reference to the actual value, you can guess whether the measurements are sufficiently and adequately having good quality, so that it can be utilized for certain applications. Now that we have discussed the confidence limits of the calibration functions, we further apply it to get the confidence limits of the calculated concentration. When we are applying the calibration function to derive the concentration of an unknown analyte in a particular sample, we can extend these confidence limits values of the calibration function to that for the calculated concentration. Concentration, say for example, if you get a signal of Y0, from that you can calculate the concentration just by subtracting the intercept and dividing that result by the slope. Y0 minus A by B. That will be the concentration of the unknown sample. Once the slope and intercept of the calibration line have been defined, we can easily calculate the concentration. Provided the measured signal, instrumental signal is within the extremities of the calibration function. If at all the measured signal is beyond the limits, either upper or lower limit, then this calibration is not suitable for that particular measured signal. You may have to do separate set of calibration and then apply. Otherwise, the associated error will be getting propagated substantially. Whenever you do a measurement, which point would be the ideal one, that we will see in the coming slides, so that your quality of measured data can be enhanced to the extent possible. And it is very important to find the error associated with the concentration, so that you can appreciate whether the value obtained as a result of certain experiment is utilizable further forward. The concentration, the uncertainty or the error in the measured concentration is calculated via the equation shown in the blue background, and the input parameters are all defined. Nowadays, we use computer softwares to do the entire calculation. You need to give only the input parameters. For example, the measured signal Y0 value, the slope and the intercept of the calibration, that also computer gives you the standard deviation as well as the confidence limits of the intercept and slope. That also we can calculate once we know the degrees of freedom and level of significance. These all are valid when the number of measurements for a particular unknown analyte is singular. That is why in the equation for Sx0 there is an expression 1 inside the square root. If you are doing repeated measurements for a particular analyte and getting the Y0 some m times, this Sx0, that is the standard deviation for the calculated concentration, gets modified or gets improved by that much factor, square root of 1 by m times, in addition to the other remaining terms. That way, the quality of measurements can be improved either by changing the number of calibration points or by doing repeated measurements on a particular unknown sample. And the confidence limits, as usual, are mentioned by the extremities of the middle value, mean value, plus minus t times standard deviation of that particular value. And the t, when you are referring to the t table, the degrees of freedom will be nothing but the total number of calibration points minus 2, since we are applying linear relationship between the independent and the dependent variable. Similar way, as we have done in the previous exercise, similar way, we can do this calculation and arrive at the confidence limits for the measured concentration. For you to get a feel of this exercise, the whole steps are described in this slide. You get a feel so that, for example, in this particular experiment, the three different unknown concentrations are giving instrumental signals in the range 2.9, 13.5, and 23. If you see closely this table and the unknown measure and signal, 2.9 is near to the lowest level, 13.5 will be around the midpoint of the calibration curve, 23 will be near to the upper extreme of the calibration curve. As I told you, whenever we are doing the calibration function for the concentration calculation, see to it that it is covering, it is including the signal within the range. If not, shift the calibration and redo the entire exercise. You people can give a try and arrive at the slope and intercept. Easy calculation is available. Any software you can use. Further, by substituting the values of slope and intercept and the errors associated with the errors, you can calculate the standard deviation of the calculated concentration using the equation given in the blue shaded box. The parameter sy by x is the y direction error, which is coming out due to the regression function. D is the slope of the calibration curve. As we are given only singular measurement units, there are no associated standard deviation for the unknown. We presume that only single measurements are done for this 2.9, 13.5, and 23 units of absorbance. Fluorescence. Okay, then n represent the total number of data points. Here again it is 7. So the degrees of freedom for t will be n 7 minus 2, 5. Y0 is the measured signal for the unknown. For example, if we are calculating the confidence limits for the lowest unknown concentration 2.9, Y0 will be 2.9. Y bar is the centroid of the calibration function. That is nothing but the average of the centroid is the point who has got coordinates x and y like that. It will be the average of the entire x values and the average of the entire y value. That is the x bar, y bar. That will be the mid, almost it comes out to be the midpoint of the calibration function. In the figure also, I'll explain in the coming slide. If you calculate the confidence interval, the standard deviation and confidence interval, you will see that at lowest and as well as at the highest concentration range, you will see that the confidence intervals are larger. Confidence intervals are larger, whereas near towards the midpoint of the calibration curve, the confidence intervals are narrower. That means the quality of the data gets improved as and when we move from either side towards the centroid of the calibration curve. So ideally, if you are sitting in and around the centroid of the calibration function, quality of data will be improved to the extent possible from the calibration. So the figure on the right side of this slide shows a typical general nature of the calibration curve. The blue line shows the fitted line, and the dotted lines on either side, either end of the blue line, those show the confidence intervals of the calibration curve derived from the intercept as well as slope and their associated uncertainties, applying the equation that particular parameter plus minus Ts for that particular parameter. For example, if we are doing intercept, yes, intercept plus minus Ts intercept. If it is slope, then again the same way. T times S on either side will be getting encompassed in the calibration curve. That much error will be there. If you see the curve closely, you can visualize that towards the end, the dotted lines on either side, they become narrower, the width become narrow. That means quality is improved. The narrower, the better. That is the concept. Okay. So these are the things we can infer from the figure on the right side. The precision of any result will keep on improving as we move towards the centroid of this regression line. Precision gets deteriorated when we move on either side. It is either side going like enlarging on either side. Because in the least square fitting, all efforts were to minimize the residuals on fitting. That is what we learned in the previous class. So the error sum will be minimum if the line passes through the center point of the entire set of data. If we want to improve the confidence limit in the calibration experiment, two ways we can do. One is that increase the number of data points. So definitely the quality gets improved. If you do repeated measurements, your skill also gets improved as well as the data refinement also takes place. And another thing is that make more number of measurements for the unknown, so that the unknown value, whatever we derive, also gets improved in quality. And in terms of the functional relationship, mathematical relationship, one can easily visualize that if you increase the number of data points, calibration data points, how it gets improved, the confidence limits get improved of the calibration function. That is nothing but you can see there is a factor called 1 by n in the confidence interval calculation or the standard deviation calculation. As n increases, 1 by n definitely gets decreased. And at the same time, when n increases, the corresponding t value which we go look for, you have seen already that as the number of repeated measurements, in the case of repeated measurements, we had seen the t table and the effect of increase in n on the values of t. Percentage value also we had seen, the t value gets decreased. So that way the width becomes narrower, quality becomes improved. In the same way, the m value represents the number of repeated measurements for the unknown or the signal y0. For example, if you do a combination of both the number of repeated measurements and the number of calibration points, it can be mathematically shown that for a fixed total number, for example, we are fixing the time duration of the entire experiment, then the total number of experiments to be conducted will be fixed. Accordingly, for a fixed total number, m plus n, the best possible precision can be achieved as and when m and n become equal. That can be mathematically also shown. That means equal number of calibration standards and equal number of replicates of the sample will give the best results possible within a certain stipulated time period or stipulated number of experiments, total number of experiments. And if you recall the previous discussions on the t values, t tables, beyond say 4 degrees of freedom, we had seen that there is only marginal improvement in the t value. So beyond 4 degrees of freedom, corresponding to 6 number of repeated measurements, which in turn will be similar for the number of calibration data, 6 number of either calibration standard or 6 number of replicates of the samples will give us a judicious control of the precision of the entire measurement data. So if you are participating in particular exercise wherein you want to prove yourself or demonstrate your quality of data, 6 is a good enough number to do practically and get enough quality data. If at all time and energy and the savings instrument along with the chemicals and all other parameters provide, then you may increase, but the increment will be only marginal in terms of the quality. However, when we go at low concentration, essentially nowadays when we use newer and newer equipments, instruments, we see that we can go down in concentration. We can try to explore smaller and smaller concentrations and get reliable data from that. However, if you see the magnitude of the variation of the signal as a function of the concentration, the natural tendency is that at lower concentration values or at lower input values, the fluctuations also will be in that range only. As we go higher and higher in the input parameter, proportionately you will see there is a magnitude increase in the magnitude of that function. That will be visible in the figure. So if at all the variation is dependent on the magnitude of the input parameter, say here it is concentration or whatever input parameter we do to the instrument. For other cases, these are for general chemistry. If you do some trigger as some perturbation or probe in the input and you get some instrument signal, whatever probe you use, if you increase the probe quantity, probe numerical value, if you are seeing proportionate increment in the variation or fluctuation, it is better to go for weighted regression rather than the ordinary regression. But what is weighted regression? That we will see now. So when we are doing single quantity measurement, weighted regressions are more suitable as and when we go down in the input variable fluctuation. But weighted regressions are a bit involved mathematically as well as stepwise also. Generally, it is applied for singular experiments only, because when you do combination experiments, the complication also arise. Accordingly, the complication also increases. So right now, we apply it to singular analyte measurement using weighted regression. Weighted regression is nothing but regression. Regression is least square fitting. Regression giving due weightage to those quantities which have got smaller fluctuations. Smaller or less the fluctuation, more weightage. That means the regression line will more closely pass through those points, so that the regression line, originally it was trying to minimize the vertical variation, residual variation. Residuals we discussed in the previous class. Here in this weighted regression, what we do, wherever the errors magnitudes are lower, relatively lower, you go for fitting the curve in such a way that these points are more inclusive, and wherever the magnitude of the errors are more, those points get lower weightage. Such variation in the dependent variable as a function of the variation in the independent variable. For example, error in the Y value keeps on enlarging as we go from lower to higher concentration region. The variation is increasing. This is called heteroscedasticity. That means hetero means different. Homo means same. In the earlier one, ordinary least square fitting, we had presumed that the variation is almost identical in the entire range of concentration. We are presuming. Whereas in real life situations, the data shows up in different region. The variation, absolute variations are proportionately increasing with the increase in the input parameter. So when the bidirection error in a regression calculation gets larger as the concentration increases, the regression line must be calculated in order to give additional weightage to those points where the error bars are the smallest. That is, it is very important for the calculated line to pass closer to that points, lower points, than to those in the higher regions. Accordingly, the deviation of the confidence interval, confidence bandwidth also gets modified. So if you see the weightage to this, if you give extra weightage to smaller concentrations, you will see that as the concentration increases, the line does not actually include the larger points. So this is achieved by giving each point a weightage inversely proportional to the corresponding y direction variance. As you see, if we are giving weightage to certain points over other, that means we are imposing certain conditions. Definitely weighted regression calculations are rather more involved and complex than the ordinary or unweighted ones. And these require many times more input parameters, that is standard deviation for the individual points. If not available, then we may have to presume some conditions. Previously, we may have to assume them conditions and apply. So the conditions or the input parameters are more in the weighted regression. The calculations are also a bit more involved. But in real life situations, heteroscedasticity is anticipated and we have to apply in order to get quality, reliable data during real life measurements. For example, how to calculate the weightage to the individual points, that is calculated by giving importance to the variances. Wherever the variances are small, they are given importance. So there will be an inverse relationship with the variance. That is why in the weightage calculation, you see that S to the power minus, there is a minus value indicating S to the power 2 indicates variance, and the minus value indicates that as variance increases, the weightage decreases. This slide explains what is heteroscedasticity in data. Homoscedasticity means the variances are equal in, variance in the residuals are equal in all the input parameters as shown in this curve. The variances are not changing as a function of the horizontal axis input. But in reality, if you increase the horizontal axis, you will see that there is an elongation, there is a cone shape getting formed if you plot the variation as a function of the input parameter. That is the real situation. That is called heteroscedasticity. A cone-like shape is formed. That means the dispersion increases if you increase the value of the input parameter. This is the real ascending fluctuation in variance during natural variable measurements. Most of the real world data goes along with this form, that is heteroscedasticity, variation as a function of input parameter. And unequal scattering is more likely in natural variable measurements. That means in reality, this situation is more frequently encountered, and whenever we go for low concentration measurements, this curve should be utilized more and more frequently. So when do we anticipate heteroscedasticity and be aware, be careful to apply, and all our efforts are to minimize the dispersion and definitely to account for the natural variation so that the random variation in the final result can be accounted for and minimized to the extent possible. So wherever we know the causes of the error, let us try to address it and get them to the minimum extent possible. So if you anticipate heteroscedasticity, where all we do observe it. For example, in data sets with large ranges, when the concentration ranges, as I told you, if you increase the number of calibration points, you are able to improve the quality. But at the same time, if you are going for larger or wider width of the concentration range, you are compromising on the dispersion of the data. So ideally, what one will suggest is that go for a smaller concentration range. Within that, go for larger number of data points. That way one can improve the quality of the data. Takes narrower range, do more number of data inputs rather than going for a larger range. Though we hear repeatedly, frequently that large dynamic range, but ideal situation will be cut it into several small pieces and make calibrations ideal in smaller and smaller fragments and utilize wherever required. So if you do go for larger range of data, you will see that the oscillations or fluctuations are much obvious and different. So what happens if you presume a particular linear relationship, it may not be valid for a larger range. Rather, you apply to small portions and get the data, quality data. And if at all there is a proportionality variation in the instrument signal, as and when we start for higher range of input parameters, the onset of fluctuation will be visible. So in that range, you go for a narrower range and get rid of this problem. Among other reasons, the nature of the variable as a function of the input parameter is a major cause. So by closely observing the experimental data, one has to have intuition to do whether go for ordinary least square fitting or the weighted least square fitting. Weighted least square fitting is applied for heteroscedastic data. And the regression models which we apply, for example, linear or a polynomial or a quadratic function, some of them are prone to this dispersion. So be aware if you are doing or applying a new model, take care of this dispersion, variation in the dispersion. Do apply theoretically first, then experimentally, then only go for the evaluation of the model. If at all the selection of the model itself is wrong, definitely you will be getting deviation from the model. As and when we apply it to larger quantity of data, you will see the deviation, and definitely the cone gets enlarged visibly. That is an indication or a caution to us that yes, here the model is to be replaced. Battery low. It can also be caused by dataset formation and inefficiency of the calculations as also. And in the weighted regression calculations, as I discussed earlier also, the weights are calculated as shown over here. And calibration parameters, namely the slope and intercept, can also be calculated. Here the input parameter called the weight of each of the calibration functions, like x is the input variable, y is the output variable. X and y also gets modified accordingly during the calculation of the slope and intercept. As you can see, the more number of parameters are to be calculated. More frequently, we use computers for doing this calculation of weighted regression. And this is a bit involved. At the same time, if you follow systematically, you can easily derive the data, because the fitted curve you get, fitted parameters, slope, intercept, and the associated errors also are visible nowadays in the computer screen itself. The weighted functions, weighted slope, weighted intercept, and weighted centroids, x bar and y bar, are calculated as shown over here. These are like software outputs directly. What happens inside is shown here. You get the ready-made data of that. If you recall the previous one, the ordinary least square fitting, we had seen that the centroid was near the mid of the calibration, in their calibration curve, and there were symmetric variation on either side. Whereas when we do apply the weighted regression, you can visibly see that the confidence interval becomes narrower at lower input variables as a function of the magnitude of the variation at the lower concentration range. So as and when we utilize instruments for measuring lower signals, where the instrument output is giving us the freedom to reduce the interval, we should judiciously utilize it and come out with better quality data, wherein this weighted regression has got importance. That is what is conveyed over here. When we are working at low concentration region, you see that the midpoint, the utility of weighted regression will give you quality data. The midpoint also gets shifted. That is, a centroid gets shifted towards lower concentration, because they are given more weightage. This is nothing but the outcome of giving more weightage to more precise data. The more precise the data, the better will be the quality. Similarly, when we do standard addition in analytical experiments, these weighted regressions are useful when we are at very low concentrations. You can see at higher concentration range, irrespective of whether you use ordinary or weighted regression, the confidence interval width are not much different. At higher concentration range, one can do either of the fitting, ordinary or weighted one. So ordinary will do, there is not much of gain in terms of the width of the confidence interval of the calibration function. At lower concentration range, preferably it will be weighted regression. For the concentration in the concentration derived from this standard addition calibration, the calculation goes like this as shown in the expression in down. If you compare the various parameters like slope, intercept, and the coordinates of the centroid deviation and the standard deviation of the calculated concentration for ordinary as well as weighted regression, all the required input mathematical expressions are summarized over here. Then the standard deviation of the slope, B is the slope, A is the intercept, and the weightage is calculated like this. This slide summarizes the entire set of equations which we have utilized for regression line of y on x, the equation being y is equal to a plus bx, x bar, y bar being the centroid of the regression line, x0, y0 are the unknowns coefficients. So now that we have understood both weighted and unweighted regression, you people all can give a try to calculate this concentration of unknown sample whose absorbances are given. Two such absorbances are given here, 0.1 and 0.6. Data are shown around 1, 2, 3, 4, 5, 6. 6 data points are there. Whatever equations I showed in the previous one, you can make use of this one and calculate the concentration. The ordinary least square fitting, we have done enough examples. You people can give a try and get the concentration as well as the spread in the calculated concentration as well as the confidence interval also. Similarly, the weighted regression also you can do, since it is a bit involved calculation. The intricate steps and their required input parameters are also defined here. Once you have done these calculations, please cross-check your answers with those given in this slide. Then you can appreciate that there is only marginal difference when you go from unweighted to weighted regressions at higher and higher concentration. The difference is visible at lower concentration, and essentially when we are working at nano or picomolar concentrations, these weighted regressions become increasingly important and their utility becomes more and more visible. So if you have to refine your data at lower concentration, definitely go for the weighted regressions. These are a list of advantages of the weighted regressions over the ordinary least square fitting. When you are working at higher concentration, there is not much of difference, but when you are doing at lower concentration, you can visually see that if you compare the calibration lines and the width of the calibration line, that is a confidence intervals, you can easily visualize that the centroid is much closer to the origin in the case of weighted regression line. That means centroid is the ideal point of the calibration function. That means values will be more reliable towards the centroid. Lower concentration values are more reliable in the weighted regression. And whereas in the unweighted one, it is near the midpoint. Here, the reason being lower concentrations where the magnitude of the errors are small, they are given better higher weightage. And points near the origin, they will be better or more suitably represented by this weighted regression. But if you take if you have a larger perspective or a larger vision, you will see that slope and intercept values are not substantially different. They are almost comparable. Unless you go for division of this concentration range into smaller and smaller portions. When you go for small partitions, the difference become more and more visible. So ultimately the both weighted as well as unweighted models give similar values for concentrations having higher absorbances, higher values. But the confidence limit of the calculations, calculated concentrations become more realistic, more utilizable in the case of weighted regression at lower concentrations. And close to the origin, those points, the weightages are high. Near the centroid anyway, the values will be more reliable in either case. Confidence intervals become narrower. The confidence interval, the narrower the confidence interval, the better is the quality of the data. So you see that the curves become open at larger concentration in either case. So in weighted regression, as y increases, the error increases, and the W0, that is the weightage falls down significantly. And for higher concentrations, as we have already discussed, both methods gives comparable error. So it is not required essentially to go for the weighted regression. Definitely lower concentration weighted regressions should be preferred over the ordinary least square fitting. Another way to evaluate whether the fitting is proper or not is the residual plots in the regression analysis. Okay, the Y residual, that is nothing but the difference between the measured and the fitted values of the Y or the output signal. You will see that these represent the difference between the measured or the experimental value and the fitted value. The smaller the difference, better is the curve. The smaller the summation of the squared differences, that is called residual sum of the squares. All efforts in regression analysis is to minimize this residual sum of the squares. If you plot the residuals as a function of the parameters, calibration parameters, if you will see that near the centroid the residual is 0. On either side the residuals keep on increasing or decreasing depending on whether you are doing weighted or ordinary regression of the function. Ideally, the residual should be normally distributed about the 0 value, but this does not happen in real cases, even though the ideal situations are not achieved every time. So this figure will explain various possibilities in real life situations. If you can appreciate this figure, if you plot the difference between the measured and the fitted values of the Y value, but the independent variable, the dot points represent the difference value. If the measured value exactly matches with the fitted one, you will see that the dots will lie exactly on the 0 line. If not, if there is a positive variation in the fitting, you will see the dots are above the 0 line. If there is a negative variation, dot will be below the 0 line. In the figure A, you can see that the dots are in this figure, the dots are much nearer to the horizontal 0 line. That means the fitting is proper. You get reliable data, and the dots are almost normally scattered on either side of the 0 line. Whereas in figure B, if you see, as the horizontal axis value increases from left to right, you see that the magnitude of the residual keep on increasing. Magnitude of the residual keep on increasing in figure B. In figure C, you see initially all the error values were negative, then much more negative. Then later on, you see that there is increasing positive value. That means the fitting is not proper. The value you need to change your model of fitting. Maybe you may have to shift from linear to some polynomial function in order to get the residuals much closer to the ideal one. That is a figure A case. In figure D, you can see that the dots are much more or less closer to the blue horizontal line, whereas one point, this sixth data point, is visibly far from the other set of data points. So if you can exclude this point, then you can say that figure D and figure A are almost comparable. But how to do this exclusion? Can we take a decision without any experimentation? No, we cannot do that. If you want to reject one of the regression data points, you have to conduct an experiment to find out which one is the outlier. This is done by this Cook's squared distance evaluation. The function is mathematically expressed over here, where yj cap is the fitted value and yji is that particular value which one we suspect, which one we suspect as the outlier. And while calculating the standard deviation sy by x, initially we include this yj cap and go ahead. And once we derive that if the CD square, that is squared distance, is greater than 1, then we come to the conclusion that the point is an outlier, reject it. Then we do the CD square calculation again and verify that all the remaining points are included in the calibration or not. That way, individual points are evaluated independently, separately, in order to see whether they are a part of this population or an outlier. We had seen outlier in separate contexts wherein we were trying to find out whether there is a gross error in the entire measurement. Here it is like originally we have presumed there are no gross error. Now we have come to the conclusion that the data follows a linear function. Even in this case, if we are finding any unexpected data, that time we go for this squared distance evaluation. Alternate way of evaluation is by flagging. While flagging, what we do is we do the standardization of the residual by dividing each of these value with the total number of measured data. Then if the standardized residuals come out to be more than 2, or sometimes the relaxation is there up to 3, then we flag means omit it as an outlier and go ahead. It is flagging is like exclusion only. And as I told you, when in the third case, figure C in the previous slide, this slide, figure C, we have seen that when the horizontal axis input parameters are increasing, you see a larger and larger deviation from the fitted curve. So that indicates that you may have to propose an alternate model to fit the data points or the calibration points. Here, alternate fitting models would be like a polynomial of first, second order, third order, or higher order. Higher order polynomials may be used for fitting the data so that the residuals of fitting could be minimized. This way, we go from linear to square to third order or higher order polynomials to get reliable data. That way, what is the maximum number of order of the polynomial you can go up to? That will be decided by the number of calibration data points in the curve. If you have n such data points, the largest polynomial possible would be n minus 1. Okay. And finally, what we evaluate is the R square, coefficient of determination. That is a regression coefficient is determined. And in the case of linear, we have seen that that is nothing but the square of the Pearson's correlation coefficient also. And the closer the R square value to 1, the better is the fitting. What we essentially evaluate is go on checking the R square value, improvement in the R square value as and when it becomes closer to 1 unity, you say that the fitting is more proper, more appropriate. But beyond certain point, you will see that there is only marginal increase in the R square value. So then the percentage increment in R square will decide whether you should go for higher order polynomial fitting or not. and the upper limit is decided by the total number of data points. And if n number of points are there, n minus 1 will be the upper limit where you have to evaluate the polynomial. And in certain cases, it is seen that monotonously R will increase. So you will be happy to go ahead with the further higher order polynomial. But a more realistic view of it will be the R prime square, that is called the adjusted R square, which is calculated like this. That is nothing but 1 minus residual mean sum of the squares of the mean sum of the squares of the variations divided by the total mean of the squares of the variation. So adjusted R square takes care of the number of degrees of freedom. As you increase the number of degrees of freedom, definitely the numerical value also goes smaller and smaller. So if you have k number of terms in the regression function, if you are increasing the number of terms in the regression function, the degrees of freedom will also get modified by n minus k minus 1. That way, there will be a check on the R square via the degrees of freedom, which will give you the adjusted R square, which was shown in the ordinary least square fitting in the very first slide of the calculation. So the adjusted R square is more realistic and utilizable term for the evaluation of fitting of a data point to the theoretical model. And the least square results, how you can understand and express to the third person. This interpretation goes like this. The closer the data points to the line predicted by the least square analysis, the residuals will be smaller. That is visibly seen by us in the previous slide. And the sum of the squares of the residuals measures the variation in the observed value of the dependent variable. And this is sometimes not explained by the presumed linear relationship. That is nothing but the residual sum of the squares of the variation. Residuals, we discussed that is nothing but the vertical deviation of the measured value with respect to the fitted value. Measured value is represented by yi, and the fitted values are represented by cap, by I cap. And when we do essentially the least square fitting of any data point, set of data points, you can see that measured value will be having some slight disagreement with the fitted value, as well as there will be some difference between the measured value, individual value, and the midpoint of the entire set of data. The difference between disagreement between the measured value and the midpoint of the data, that is called the total sum of the squares, is calculated. It is nothing but the summation of the difference between the measured value and the midpoint value, then the square, and sum it. That way, the total sum of the squares are calculated. And whatever is the difference between the total sum of the squares and the residual sum of the squares, that is the explained variation. That is nothing but the variation due to the regression function, which we presume while doing the iteration and deriving the data. So the total variation is nothing but the difference between the measured value and the centroid. The difference between the measured and the fitted value, that is the residual. The remaining, the difference will be the variation due to regression, which is not explained. That means the regression leans. If this variation due to regression is significant, that indicates you need to do alternate model to fit the data points into. And the F values we normally calculate by taking the ratio of the mean squares of one function to the error squares. So the squares due to regression is called the error sum of the squares. So if you take it in the denominator and calculate the F value, the way the calculations proceed similarly when we did for the variance ratio test also, the F values can be calculated. And if the calculated S value is coming out to be more than the critical values of F for the corresponding numbers of degrees of freedom, then we can say that there is significant, if the calculated F value comes out to be greater, then we can say that there is significant variation due to regression. That means the regression model needs to be re-verified and maybe reassigned also. If the calculated value comes out to be less than the critical value, then there is no significant difference. The regression is acceptable. We can go ahead with the null hypothesis. This procedure is exactly same as we had discussed in the F value calculation earlier also. So a significant regression is one in which the variation in the Y values due to the presumed linear relationship is large and the F values will be small. But when the regression is significant, then we will see that F values are visibly different from the tabulated F value. These regression functions can be used not only for calculating the concentration, we can see the agreement or disagreement between two methods. Which say, for example, there is an already established method and we are trying to propose a new method. If we have to see whether the new method does agree or disagree with the existing method, we can check via the regression line. So the referee method is taken on the horizontal axis and the new method or the proposed method values are taken on the vertical axis and the values are compared. If both the methods give identical results, the line will pass through the origin and the slope will be same. Slope will be almost 1. Slope of the curve will be 1. If at all there is a difference between the measured and the proposed method and the referee method, you will see that there is a constant difference. It will be the case in the figure B. If some signal is not being measured by the proposed new method, you will see that there is an intercept in this regression line. Whereas if the proposed method is having lower slope, lower precision than the actual reference method, you will see that the slope gets decreased. The figure C is the combination outcome of both B and D. If at all there is some point wherein one of the methods is blind, you will see some variation in the line, and essentially the variations are visible at lower concentration range. If at all more than one species is present in the system and one of the methods is blind to such species, such combination species, you will see unexpected results, sometimes scattered data on either side, sometimes only one method will give you reliable data, other method is almost blind to the signal. Sometimes one method will be having higher signal, other method will be having lower signal also. This type of unexpected observations are observed during the comparison of two methods when more than one species are visible, are present in the system, and one of the methods is not having sensitivity to the particular different species. Here we will stop. In the last class, we had discussed regarding ANOVA, and we found that there is significant difference between two observed set of data. If at all you come to the conclusion during ANOVA, there is a significant difference between the set of data. Which data is causing the difference? That can be calculated using this least significant difference method, wherein we take help of the T values as well as the other parameters, total number of measured quantities and the mean square of the errors. And the F-test, if F-test disqualifies, if F-test says that null hypothesis is to be rejected, then we go for checking which parameter, which input parameter is giving that variation. That is done by this least significant difference method. To the next class, we will discuss here onwards. Let us see if there is any clarification in the chat box. While checking the chat box, let me summarize. We had started with the ordinary least square fitting, then we went ahead with the weighted regression and calculated the concentration, the slope intercept, their variations and the concentrations, confidence limits of both ordinary and weighted regressions. We saw that when to use weighted, when one can use either of the regression weighted or unweighted. Depending on the input parameter range, we can take a decision when to go for a weighted one, when to go for the ordinary least square fitting. And whether the fitting is appropriate or not, that can be visualized via the residuals plot also. The variation in the residuals plots, from that we came to know if at all there is an outlier, how to address the outlier, whether to retain or reject one particular point. And from there we went ahead with doing application of the curve fitting to non-linear relationship also. Then in the last slide, we had seen that if at all there is a disagreement between set of data via F-test, how to carry out, which of the data points is causing the disagreement, can be addressed that particular point and get rid of it via this t-test. Once F-test is done, you come to the conclusion whether t-test can further define the data. Till this point we discussed today. Tomorrow we will see a real utility of this least significant difference. As there are no doubts written in the chats, we will wind up for the day.